In this video, we're going to talk about exponential growth and decay and logistic models. So here we have the equation for exponential growth and decay. So A of t is the amount of whatever substance is left after time t. A naught, or A to the subscript of 0, is your starting amount of that material. E is a constant. We've worked with that before. K is our growth or decay rate. So if K is positive, that's going to be a growth rate. And if K is negative, then that is going to be a decay rate. It's going to decrease. So K is always written as a decimal, which is the equivalent of a percentage. So if it's 70%, it would be 0.7. So beware of that. And T, as always, is time, but pay attention to the units. So make sure that everything matches. If it's all seconds or minutes, just be very careful, because sometimes you have to convert. And so if you look at exponential growth, it's going to look like something like this. It's an increasing function. And exponential decay, of course, on the other hand, is going to be a decreasing function. So now let's look at an example of exponential growth in bacteria. So let's say a colony of bacteria that grows according to the law of uninhibited growth is modeled by the function given here, so n of t, and where n is measured in grams and t is measured in days. So there are a lot of things that we can analyze about this. So let's work through 3 of these and move on to some more interesting questions. So our first question is, let's determine the initial amount of bacteria. So I take the original equation that I know is about exponential growth and decay, and I realize that this number right here, this 100, is my A naught. And in terms of n, because we're using n here, not A, that is the same as n naught, or at time 0, that's how many grams of bacteria I have. So it's 100 grams of initial bacteria. And the next thing I need to find is the growth rate of the bacteria. So using that A of t equation that I happen to know, I know that 0.045 is going to be my K. So I just translate that to a percentage and I move the decimal point 2 places to the right. So the growth rate is 4.5%. And another thing I'm asked to find is, what is the population after 5 days? So t is already in terms of days, and it's asking about 5 days, so I just plug in 5 for t, and I use the e to this power function in my calculator, multiply that by 100, I get this really long decimal, so I'm going to round it to about 125.2323 grams. And now I'm asked to find how long will it take for the population to reach 140 grams. So t is the thing that now I'm looking for, the time that it takes. So I'm going to replace this n of t, which is the resulting amount, with 140, because that is the resulting amount I want. I just am now looking for t. So the first thing that I do with this equation is I divide it by 100, because I need to get that e to some power by itself. So I have a quantity of 140 divided by 100, which I can actually make 1.4 if you really want to. Now my next step to get rid of e is to apply ln to both sides. So when I do that, ln of e is 1, and that actually just eliminates this. So I just bring this guy down, so 0.045 times t is equal to the ln of this side, because there's no e there, it won't go away. So ln of 1.4 is equal to this quantity, and if I divide by 0.045, I will get t by itself. So I'm going to use my calculator to do this. And so when I use my calculator to find this calculation, I get approximately 7.4772 days. So that's how long approximately it takes to have a population of bacteria that reaches 140 grams. So now one last question about this bacteria. What is the doubling time for the population? So how many days, right? What is that t value? That means that I get twice as much that I started with. And if you remember, we started with 100 right here. So that means that I'm actually going to set this equal to 200, because that is twice times 100. So I start with this equation, which is a lot like the last one, and I'm going to apply the same steps. So I'm going to divide by 100, so I end up with 2 here, and I'm going to apply the ln. And so the ln of e crosses out. I bring down this exponent here. So t is going to be equal to ln of 2 divided by 0.05. And I put that into my calculator, and I get an approximation here that's 15.4033 days. So that's about how long it's going to take for the bacteria colony to double in size. So moving from uninhibited exponential growth, let's talk about uninhibited exponential decay. And to specify, let's look at radioactive decay. Now, you may have studied this in science class before, but our same equation here is the same as growth and decay. So we still have the A of t, A naught, E, and then K t. But this time K is less than 0. So if you have a negative exponent, that's going to create division instead of multiplication. So as a reminder, some things about radioactive decay is that all radioactive substances have a half-life. And using carbon dating, we know that carbon-12 and carbon-14 exist in all of those materials. And after something dies, carbon-12, that amount remains the same, but carbon-14 decays at a certain rate over time. So that allows us to carbon date and figure out how long this thing has been dead for, which is fun. So let's try an example. And let's let that example be estimating the age of ancient tools. So traces of burned wood along with ancient stone tools in an archaeological dig site in Chile were found to contain about 1.67% of the amount of carbon-14 that it originally started with. And if the half-life of carbon-14 is 5,600 years, let's find out approximately when that tree was cut and burned. So I would love to just plug that into an equation and find the amount of time, or t, but I don't have k, I don't have my decay rate, so I have to find that first. So here's what I know. I have my original equation here. I know that the time it takes for the half-life of carbon-14 to degrade to half of its amount is 5,600 years, so I'm going to plug that in for t, and I don't need to know how much carbon-14 I have, but I know that the ratio of what I started with versus what I ended with is 1/2 of what I started with. So that means that whatever this quantity is that I started with, I'm going to take 1/2 of it. So I can still use that variable in there. And luckily for us, with multiplication and having the same variable on each side of the equation means that I can just get rid of those two things. Now I'm going to apply ln to both sides because, see, I just have that e to a power left over. Let's do that and find out what k is equal to. So I apply ln, the ln and the e cancel, and I divide each side by 5,600 to get that k, or that decay rate, by itself. So this quantity, ln of 1/2 all over 5,600, is actually my decay rate, or my k. And I'm going to leave it here because I'm going to need it in another equation to find out when this tree was cut and burned. So the problem with approximating a decimal inside a problem and not at the end is that your final answer could be off by a couple of decimal points, which, in the grand scheme of things, kind of matters here. And so if I insert my k value back into this equation here, here's what I have. And now I'm looking for t, but I've got a couple other variables I need to figure out. What I know about this tree is that 1.67% of the original carbon-14 is left in it. So just like what we did here where we didn't need to know what A naught really was, I know that I don't have half of it left, but I have 1.67% of the original amount left, which on the left side of the equation is going to look something like this. And so that allowed me over here to cancel my A naughts, which I'm going to do over here as well. So now I just apply ln to both sides here, and I solve for t. So I have ln of that decimal quantity is equal to this whole thing that we solve for over here, so k times t. And you can divide this ln of 0.0167 by this quantity, or you can multiply by the reciprocal of the fraction. So that's what I did here. And I got t to be about 33,000 and something years ago that this tree was cut and burned. So a little longer than I've been alive. And the last concept in this video that I want to talk about is something called a logistic model. So in exponential growth and decay, so with bacterial growth and radioactive decay, those are uninhibited, meaning that they can grow and decay forever. But a logistic model has to do with inhibited or limited growth or decay. So there's a point at which it will stop or it will level out. And we model a logistic model using this equation. So A and B are some constants. T is always time, E is our constant that we use, and C is really important. That's what we call carrying capacity. So for example, in a population, there's always a certain limit that a population will hit. It will not grow forever and ever and ever and ever. It will hit a carrying capacity. So it's always this line y equals c. So if it's growth, it's going to look like this, and if it's decay, it's going to look like this. And here are just a few more things to keep in mind, especially when you look at a graph of a logistic model. So the domain for any logistic model is going to be all real numbers, but the range goes from 0 to c, whatever that carrying capacity is. And there are no x-intercepts, and there's only one y-intercept at p of 0, so when x equals 0. And there are two horizontal asymptotes, so one at y equals 0 and one in y equals c, carrying capacity. And that the function is increasing, so this is the increasing one, when b is greater than 0. So note that the original function in the last slide had a negative in front of the b. So if it was like negative 0.5, it would be an increasing function. But if that b in the equation is a positive number, so right, you have to switch the sign because it's negative b. So if you have a positive number where that b is, so it's like e to the 0.5 something, it's actually going to be a decreasing function, just in the way that the original works. You can always graph it, and it will be obvious if it's increasing or decreasing, if you can't remember that. And some other things, the inflection point is 1/2 of the whole y-axis that it takes up. So that's 1/2 of the carrying capacity. And it does something like changes its concavity. So this would be concave up and that would be concave down. That's something you'll explore more in calculus. So hold on to your seats for that one. And also this graph is smooth, continuous, no corners, no gaps, no weird stuff going on. And now let's talk about fruit flies, everyone's favorite. So let's say fruit flies are placed in a 1/2 pint milk bottle with a banana for food and yeast plants for food and to provide stimulus to lay eggs, because of course we want more of them. And suppose that the fruit fly population after t days is given by this equation. So we're going to do a multi-step thing here. So the first one is to identify the carrying capacity and the growth rate. So I looked at my equation, and for the carrying capacity, that's always my C value. That's the number on top. So carrying capacity is 230 fruit flies. And then for the growth rate, I looked to this B value here. So remember, if it's actually negative, it means that it's actually growing and not decaying, so it's going to be an increasing function. So I take the absolute value of that, and it's 0.37, and I multiply it by 100 to get a percentage, and so that's 37% per day. And now my second step is to determine the initial population. So that's when time is 0. So I'm going to plug in 0 for t and figure out what that's going to be. So I use my calculator and I actually get a nice number. So it starts with 4 fruit flies. And now I want to know what the population is after 5 days. So just like when I wanted to know when it started at t equals 0, I'm just going to plug in 5 for t and see what I get. And so when I plug in 5, I don't get a nice even answer. I get 23 point something. So I'm going to round down because I really don't want to count a quarter of a fruit fly. So that's about 23 fruit flies after 5 days. So next I want to know how long it's going to take for that population to reach 180 fruit flies. So I'm not plugging in for t, but I'm going to plug in 180 right here, which is my amount that's left over. So 180 fruit flies goes here, and now I'm searching for t. So I set this equal to 180, and it's equal to a fraction. So I put 180 over 1, and I'm going to cross multiply. So I have 180 times this quantity, all right here, is equal to 230. So my next step is to isolate everything until I can get a t. So what I'm actually going to do first is divide by 180 on both sides. So once I do that, I get this quantity, and now I have to subtract 1. And I get 5 over 18ths, and now I'm going to divide by 56.5. So now I have something that is e to some power with a t in it is equal to whatever's on the other side. So 5 over 1017, which I use my calculator in math frac. Please use that in these kind of problems. So now I have my e by itself, and in order to get to that t, I've got to apply ln to both sides. And once I do that, it eliminates the e and the ln on that side, so all I'm left with is negative 0.37t is equal to ln of 5 over 1017. So I'm going to divide each side by negative 0.37, and I'm going to use my calculator. I'm going to get this long decimal. So that means it's going to take about 14.4 days for our population of fruit flies to reach 180. And the last thing that we're going to do here is we're going to break out our graphing utility, so Desmos or your calculator, and we're going to graph the original function, so that's the curve you see here in blue, and we're actually going to graph the line of y equals 115, which is 1/2 of the carrying capacity of 230. So if you remember a couple slides back, that is our inflection point. And although this function is still increasing to the left and the right of the inflection point, the type of increase actually changes. And what that means is that on the left-hand side of the inflection point, although it's still increasing, the population is increasing at an increasing rate. But once it hits its inflection point, it's still increasing, but it's increasing at a decreasing rate. Now, that doesn't have to make a whole lot of sense to you, but once you take calculus, hopefully that will make a little bit more sense. And that's going to do it for this video. Thanks for watching.